Hello everybody. We have been discussing the motion of a rigid body, and we have discussed two ways of representing the change of orientation of a rigid body. And let me remind you a little bit about that. So this, what I'm drawing here, is a set of axes. I will not even label them as x, y, z, but this is what we call the space set of axes. And we said that we'll choose the space set of axes such that it is kind of aligned to the principal moment of inertia. We'll come to principal moment of inertia and moment of inertia of a rigid body when we discuss the mechanics of the rigid body, but I presume that you know of these a little bit. So at t equals to 0, we assume that the rigid body is, so I'm drawing the rigid body in this particular fashion today for a reason. And this is the rigid body, and initially these are the three body set of axes, and these three axes are chosen along the principal moment of inertia of the rigid body. So I align the space set of axes at t equals to 0 with the body set of axes. So now the body set of axes has a different orientation at t equals to say t1. But that is all right. That is the motion that we are talking about. And this change from there to there, we denoted by either the A matrix or the other matrix. So this is given by a t. So at or a t1, and you can imagine at the initial point, this is at a t equals to 0. It's the initial configuration, and with respect to the initial configuration, we describe all the other configurations. So this must be the identity matrix. The initial configuration is the initial configuration itself. So this is what we said about the change in the orientation of the rigid body. So in general, A, which is the rotation transformation, can be represented now in different ways. So let us just talk a little bit about the SO3 representation. And one way we can represent it is using the Euler angles in the SO3 representation. And that we said that, this is usually is given by a X convention, which means that I do a first a rotation about Z axis, then rotation about modified X axis, and then again rotation about Z axis. And the first rotation is given by phi, this second rotation is given by theta, and the third rotation is given by psi. So these are the three angles, three names we have chosen. You can choose anything as you want, but this is what we had chosen. Now, when I say A is a function of t, so A being a function of t essentially means that all these parameters, 3 degrees of freedom specifies the motion of the rigid body, they are all function of t. That is what I mean, right? Now, today we will look at one more way of showing the motion of the rigid body, and to motivate that, we'll start with a theorem and we'll prove the theorem, and then we'll proceed from there. Okay, so this is what you already know. So let me come to the theorem now. And most of the things initially was done by Euler, so this is a theorem by Euler. It says the general motion, we'll dissect the theorem once we write it down, but let me just write it down first. the general displacement of a rigid body with one point fixed is a rotation about some axis. Okay, so let us dissect the theorem. So we are talking about general displacement of a rigid body. Well, general displacement of a rigid body, we have talked about it many times, has 6 degrees of freedom. To start with, if I just talk about the general displacement of a rigid body, it has 6 degrees of freedom. But then we said that one point, or Euler said that one point fixed. That means to fix one point in the rigid body, I need 3 constraints. Okay, so that leaves me with 3 degrees of freedom. 6 minus 3, you will agree, is 3. Okay, now that Euler says is that given by a rotation about some axis. Okay, so now if I want to fix an axis, in 3D space, 3-dimensional space, that you will say that will require 2 numbers. So fixing an axis is like fixing a unit vector, right? Now this is a vector, so it should have required 3 numbers in 3-dimensional space, but you have already specified that its magnitude is unity because it's a unit vector, so that reduces 1 from 3, so you require only 2 numbers. So once you have fixed the axis, you need to know that how much is it rotated about that axis. So that's one rotation about the above axis, and that gives you 1 degrees of 1. That to specify that you need one variable, so again you get finally 3. So that works out. So these two things matches. So the Euler's theorem must be right, but obviously this doesn't prove the Euler's theorem because we just have counted the number of degrees of freedom required to describe the general description, the general displacement of a body with one point fixed is same as the number of degrees of freedom to describe the rotation about one axis, but that obviously doesn't prove that it's a rotation. Okay, so what do we do? Let us try to see if we can prove Euler's theorem. And for that, we'll need a mathematical description of it first, because we can prove things easily if it has a mathematical form. So, a mathematical description of the Euler's theorem. So what we are doing, we are rotating a rigid body with one point fixed, right? So now if I have r as a vector, r is a vector, I can represent this by a column matrix. Right? A is an orthogonal matrix. So I know that this gives rise to rotation. This we have seen in a couple of lectures ago. So rotation means r prime, or if I can write this way, r by rotation goes to r prime, which is given by a times r. This is what happens in a rotation. Now any displacement can be written this way. We have already seen, because we assumed that it's a rotation, that can be written this way, but any displacement I can write this way. So r changes to r prime by some matrix A. Okay. Now, okay, so I must clarify that by displacement I mean change in the state of the rigid body. Okay. Now what Euler is saying is a change for the rigid body with one point fix is such a change where there is an axis of rotation. First of all, see, if there is an axis of rotation, any point in that axis we know by rotation does not change. So that if I have an axis of rotation, which is say this one, and I have some rotation about this axis, I have an origin which is the point which is fixed in the rigid body going inside the axis. If I take any other point in the axis, say this one, and take this vector and take this vector as r, this rotation cannot change that vector, right? So Euler's theorem is telling you if A is a rotation, right? A is a general displacement, as I said. We know that the rotation can be written this way, but any displacement can be written this way because any displacement relates the new xyz with the old xyz by a matrix. Whatever is the relation, you write it in terms of a matrix. But if A prime is a rotation, there exists a spatial r, just like what I have shown here, which is an r along the axis, for which r prime, which is nothing but A times r. So I will write the matrices with a bar on top and the vectors with the usual vector sign. this will not change, so this will remain as R. Now if we dissect this further, we see what we get. The requirement is the existence of an R such that A R equals R. Now this looks is quite similar to the eigenvalue equation for a matrix. So A times X is lambda times X, right? With the, so these are the, this is the eigenvalue, and this is the eigenvalue equation. So if you see the Euler's theorem now, it essentially is telling you, okay, so this lambda is the eigenvalue and X is the corresponding eigenvector, right? I am assuming for this lecture that you have fair amount of knowledge in matrix algebra, not an advanced knowledge, only fair amount of knowledge. If you have any problem in understanding certain statements that I make here, because I assume the knowledge in the matrix algebra, please note that down in your doubts and we can discuss that further. Okay, so this is called an eigenvalue equation where lambda is the eigenvalue and X is the corresponding eigenvector. So if I compare this with that, then the mathematical statement reduces to, Euler's theorem reduces to the fact that rotation matrix will have one eigenvalue What is the eigenvalue? Well, if I compare these two, it is obvious that the eigenvalue is 1. One eigenvalue equals 1, so lambda equals 1. So, see, this is a 3 cross 3 matrix, SO3 representation. So, SO3, A is a 3 cross 3 matrix. So, it has 3 eigenvalues. Right? So I call the lambda 3 as 1. You can call any one of them as 1. So I just choose the third one as 1. And that is not the only thing. The other thing that you realize comparing these two, comparing this with this, is that the direction, the eigenvector, is essentially giving you the direction of the axis of rotation, because that is what remains unchanged in this operation. The corresponding eigenvector gives you the direction of rotation. of the axis rather. We'll see that it's the direction of rotation also, but for the time being, it's the direction of the axis or defines the axis. And eigenvector, you know that if you multiply it by 2, it's still the eigenvector. And that is all right, because if this is my r, if I multiply it by 2, it still remains on the axis. So that gives you the x, the corresponding eigenvector gives you the direction of the axis. Okay, very nice. So let us, before we go further, before we try to prove this statement now, we have got this mathematical statement. So what all we have to show is, now to prove Euler's theorem, we have to do this. To prove Euler's theorem, we need to show A has at least one eigenvalue equals 1. This is a very interesting set of developments that we have done so far. So let me go back to these and show you, because this is something that you need to do in many cases in physics, and we realize it here very nicely. Euler gave a statement which is not in mathematical form. It's just a statement, and we kind of heuristically showed that it should work. But then, by doing a set of operations, set of arguments, we have now come to a mathematical statement. And this is something very precise, and this can be proven easily. A statement like the Euler one, to prove this, it is much more difficult. But when I set it in terms of a mathematical form, where I say, okay, so I know what type of matrices A can be, they are the orthogonal matrices. Now, all I have to show to prove the Euler's theorem is that the orthogonal matrices have at least one eigenvalue. That's all. That will prove the Euler's theorem. And that is a fairly easier statement to prove. Now, before I go there, let me tell you some properties it will have once I prove it to have one eigenvalue. So let us look at the properties such a matrix A. So first thing we have already discussed, SO3 representation A, 3 cross 3 matrix. So it has 3 eigenvalues. So let us call them lambda 1, lambda 2, and lambda 3. We know A is orthogonal . It's rather special orthogonal. So determinant of A equals 1, right? Now, this is something that comes from matrix algebra. I guess that you know it very well. Determinant of any matrix is nothing but the product of their eigenvalues. So this is lambda 1, lambda 2, lambda 3. And this remains unchanged in a similarity transformation. Similarly, the other thing that remains unchanged is the trace of A, and that is always given by lambda 1 plus lambda 2 plus lambda 3. This also remains unchanged. Now, because it's an orthogonal matrix, we already know that the determinant of this is equals to 1. Now, which means if lambda 3 equals to 1, which is what we are going to prove, one of the eigenvalues is 1, then lambda 1 times lambda 2 must also be 1, which means if lambda 1 is complex, lambda 2 must be equals to the complex conjugate of lambda 1. Because the multiplication is real, is plus 1. If this is real, if lambda 1 is complex, then lambda 2 not being, if it is not its complex conjugate, then their multiplication cannot be real. And if lambda 1 lambda 2 is not real, then lambda 1 lambda 3 lambda 2 cannot be also real. So most general way of writing the three eigenvalues then is lambda 1 I write e to the I phi, it's a general complex number. Lambda 2 I write e to the minus I phi. These are I write with capital phi, we'll see that why I write with capital phi later. And you see that satisfies the fact that lambda 1 times lambda 2 is 1 and lambda 3 will prove to be 1. And in that case, it is automatically satisfied that lambda 1, lambda 2, lambda 3 equals 1. And in this case, trace of A is 1 plus e to the I phi plus e to the minus I phi, which is 2 cos phi. I don't need this here. Okay, so these are the things that I am going to get shortly. So let me just prove it and get them. To prove, so what I am going to prove? I am going to prove that A, which we know to be an orthogonal matrix, if it is giving a rotation, I have to just show that it has at least one eigenvalue. One of the eigenvalues is equals to 1. Okay. To do that, we start with an identity. So A minus the identity matrix times A transpose. What will these be? Well, A is orthogonal, A transpose is I, and I times A transpose is nothing but A transpose. Okay, and I take determinant in both sides. So if I do that, what will I get? Well, this is determinant of product of two matrices, that is product of the determinants. So I get determinant of A minus I times determinant of A transpose equals determinant of I minus this. But you see, this is 1 because A is an orthogonal matrix. So the left hand side just becomes determinant of A minus I. In the right hand side, to evaluate the right hand side, what I do is I know that determinant of a matrix is same as the determinant of its transpose. So I just take the transpose of this inside. So what I write is the transpose of this. As the transpose of this is, transpose of I is obviously I, and transpose of AT is A because it's an orthogonal matrix. So you are left with a form where in the left hand side I have determinant of some matrix say B, and in the right hand side I have the determinant of the matrix which is minus of B. Okay, and remember that B is, in my choice here, A minus I is a 3 cross 3 matrix. Now it can be shown very easily for n cross n matrix minus of the determinant of B, so matrix B, equals determinant of the matrix B for n even, and equals minus of the determinant of matrix B. This you can try to prove. This is very straightforward, and the way you prove it is write the matrix in its diagonalized form. You know that the determinant does not change if you do a similarity transformation, so you can write the matrix in its diagonalized form, change all the diagonal element with a minus sign, that will give you the minus of the matrix, and then try to prove this. And this is for n odd, which for our case we get, where n is equals to 3, which is an odd number, we get determinant of minus B equals minus of determinant of B, which in turn, let us write from there, determinant of A minus I is equals minus of determinant of A minus I, which implies 2 into determinant of A minus I is 0, or determinant of A minus I is 0. Okay, now this is what I got so far. Okay, now we need to go back to our knowledge of matrix mechanics a little bit to understand what we have got. So for any matrix, say let us call any matrix B, the secular equation which gives you the eigenvalues is given by determinant of B minus lambda I equals 0. So you can try to write it down in terms of the components, say Bij of B. Ij goes from 1 to 3, and you will see what the secular equation looks like. And this equation, so let me write it down because that will give us the insight. So B11 minus lambda, the diagonal components will have this minus lambda I because I is diagonal only, B22 minus lambda, B33 minus lambda, and you have B12, B13, B23. And you have to do the determinant of this, and that is set to 0. So that is the equation that gives you the eigenvalues lambda. Now, this will have 3 roots as lambda 1, lambda 2, and lambda 3. So that is what we discussed earlier. And now you see, if I compare this equation with this, then we already see that this has one root of lambda equals 1. Right? So if I put lambda equals to 1, obviously this will satisfy if B is equals to that matrix A. So that shows us that we can prove Euler's theorem. That's essentially the proof of the Euler's theorem. Okay. So once I have proven this, now the Euler's theorem holds. Now that has been shown explicitly, and all these propositions that I wrote down from 1 to 5, they also hold. Right? So we know all these propositions now hold. So I can write down the 3 eigenvalues. So a general way of writing the 3 eigenvalues of A is e to the I5, e to the minus I5, and 1. So this is one point that we have got so far. The other thing is that the axis of rotation this I will write as capital phi, okay, with those bars at the ends. Is the eigenvector, or better to say is along the eigenvector corresponding to the eigenvalue 1. That also you have seen. Okay, so if I can write down, so it means that it implies that if I write down a rotation okay, before that let us see that this is 2 numbers I require to specify that, and one number here which is 5, which I have here. So this phi is essentially will give you the rotation, because the axis of rotation will require only 2 numbers to fix. So this phi will give you the rotation, right? So if I write a rotation about, I have chosen x lambda 3 to be 1, so about the third axis or the z axis. This is just because I have chosen lambda 3 to be 1. If you have chosen lambda 1 to be 1, I would have chosen a rotation about x-axis, because that's the axis which is the axis of rotation according to the point star 2 here. And how much will be the rotation? Well, I have that parameter phi already by an angle phi. this will be the this this will be change in the orientation or the displacement of the body. So let us write that. So I call that T phi about z, and we know how to write it down. This is cos phi sine, I am writing capital phi, you know why, that is the parameter I have chosen, and everything 0 except here I input 1. Okay. So that is the A that I am supposed to have, and just check what is the trace of A. Trace of this matrix, okay, inputting that bar, is 1 plus 2 cos phi, which is what you expected. So indeed, that capital phi, which came out just by writing these two complex numbers over there, is the amount of rotation. Now remember, this was our Euler matrix in terms of those three rotations, z, x, z convention, x convention with z, x and z. And this is what I will use now to find the trace of this. Okay. And obviously I will not be able to show you this, but please try to figure out what is the trace of this, and which is straightforward. I will just write down the result directly and then we will discuss. Okay, so here I have written down, calculated and written down the trace of A. So this is straightforward to do. You can obviously do it. This must be equals to 1 plus 2 cos of this phi. This is a capital phi, this is a small phi. So this doesn't have those bars. So what is the left hand side? What is the right hand side? The left hand side is given by a single rotation about a chosen axis. Okay, so let me call this, we are calling this, let me call this z prime. Okay, some chosen axis z. So it's only one rotation which is giving the displacement of the rigid body about that fixed point in the rigid body. The right hand side, what we have is the same rotation given by three successive rotations about three different axes. Okay, so that is how we got the Euler equation in the first day of discussion on the rigid bodies. On the right hand side I have written the trace out of those three simple rotations. In the left hand side I have written the trace out of one simple rotation. Right? Now if I add 1 to both the sides, this can be written more compactly. The left hand side becomes 2 into 1 plus cos phi. And the right hand side becomes 1 plus cos theta times cos of psi plus phi. And you can check, this will boil down to cos phi by 2 equals cos of phi plus psi by 2 is just using the cos square theta by 2 is 1 plus cos phi, cos theta, that formula. This, the only thing is that I can choose a plus sign or minus sign, because what comes is the square on the left hand side is the square of the right hand side. But then you will expect that if there is no rotation, so no rotation, means that phi equals 0. So this left hand side will 1 and the right hand side will also be 0. So phi equals psi equals theta equals 0. So if we would have chosen the, okay, so if capital phi equals 0, the left hand side is 1. And if all these are 0, then the right hand side is also 1. If I would have chosen the minus sign here, because what you get is a square of the left hand side as equals to the square of the right hand side. I could have chosen a minus sign in the right hand side or the left hand side. But if I would have chosen a minus sign, the left hand side will become negative 1, but the right hand side will have minus 1 times minus 1, it will be plus 1. So this will not be satisfied. So this condition will not give the left hand side equals right hand side. So we chose the positive sign. So that we have learned how the general displacement of a rigid body about a fixed point can be given in terms of a single rotation about an axis. We'll use that in the next lecture. Thank you.